So keep in mind that we're not really doing new information. We're just building on information you've already done. We're putting two things together. We're putting together ice charts with pH. So it's just a few extra little steps. You have already used ice charts to solve for Ka. And the way you've done it is once you've gotten the reaction and once you figure out what goes in the equilibrium row, you just put, these will be like actual numbers. In this case, the water won't matter, and those will be actual numbers. And you just put them in that K expression, and then you do some solving. It's the same idea for this one. We're going to end up being able to figure out the numbers at equilibrium, and then we'll be able to plug them into the K expression. So you've already done this. We're just now doing it with a little tiny twist. So the information that's different is that instead of it just telling you, oh, this is the equilibrium concentration, it tells you the pH. pH is a sneaky way of telling you equilibrium concentration. The pH of the solution comes from the acid reacting with the water, making H3O plus molecules, and those H3O plus are what are registering on like a pH meter or a pH paper or indicator or whatever you got that's telling you got a pH. Usually a meter is the one that gives you pretty good numbers like that. So I'm using just a generic HA acid. A represents anion. I don't know. It just is something that's negative, and it has an H on the front there. So this is our generic way of just saying acid. And this is a weak acid. I have to tell you is a weak acid, but this is a weak acid. We're only going to be solving for weak acids this way. Part of the reason behind that is because we already did strong acids last time, and strong acids dissociate completely. They don't have a back and forth arrow. They completely break up into these two parts. Weak acids are what you have to use Ka with because they don't break apart completely. Only a little bit of them break apart. That's why vinegar or balsamic vinegar on your tongue does not burn your tongue, but it tastes sour. If balsamic vinegar completely broke apart into its positive and negative ions, then you would be burning your tongue with like horrific acid if it all broke apart. So this, because it's an acid, is going to give an H to the O, and it's those electrons in the O that help hold it on, and it comes over as H plus, so it becomes H3O plus, and then we have left over the A minus. The order of this doesn't matter. Those are AQs, and then that's a liquid. So note that we are not going to put anything at all in that column, and we're going to completely ignore it. So we know the initial is 0.25 molarity. These don't have any because initially nothing's happened. The nice thing about weak acids is you almost always, and I'm not going to say always, but like almost always, like 98% of the time, all the coefficients are 1. That makes all of the math with this really nice also. And then we know at equilibrium, we have 25 minus x, we have x, and we have x. So if we know what x is, we can figure out this, and this, and then put it in together for the K expression. And you've heard me say this before, but it's always a good idea to go ahead and write the K expression, even though I didn't first. You should always write it first. So that's my K expression. Again, remember, water's liquid, you don't put it in it. So before I put anything in my K expression, I need to know what it is, and that's where pH comes into play. So pH is like a weird, tricky way of saying H plus concentration or H3O plus concentration, because remember, pH is equal to the negative log of H3O plus, right? Well, if I want to know what is H3O plus, the other formula is 10 to the negative pH is equal to H3O plus. So I don't need this equation, I need this one. But those are not new. You did them last time before the test. So we're just going to take this, and we're going to use it to figure out x, and that x. I'm going to bring over my calculator, and I'm going to say 0.25. I'm sorry. Let me actually do my math there. It's 2.6. So 10 raised to the negative 2.6 is H3O is equal to 0.002511. And I would generally try to keep that in your calculator with a whole lot of those extra digits. I might actually put the 9 in there too, because you're going to have a better number. So into my equation over here, I have it's going to be that number times itself, because both of those are x. 0.0025119. So that number squared in my calculator already. So that's nice. Keep it in the calculator. Just keep using it. Enter. And then this is 0.25 minus that 0.025119. And here's what's really nice about it. Let me show you what I can do on this calculator. So I've got that number divided by parentheses 0.25 minus, and look, I'm going to just tap it. In your calculator, you can also go up and like grab it, but on the digital calculators, you can just tap it. See, I just tap that number with my finger, and there we go. So that tells me that my Ka expression, which was my answer, is 2.55 times 10 to the minus fifth. We'll tell you how many sig figs to put in here. In this case, because my pH had that number, the sig figs, it's going to get a little bit too small. So I wanted to just show it to you with all of these sig figs.